All right. OK, well, thank you, everyone who showed up for coming. As I'm sure all of you know, this talk is on behalf of Rho Beta Epsilon. And my name is Peter Matrano. And the title of this talk is /main.cpp. Why it's named that will become clear in a minute. So why don't we just dive in? Let's ask a simple question, or at least what should be a simple question, which is, how do I run this? OK, so raise your hand if you know. Or you think you know, like you're pretty sure you know. I know you know. I know for a fact that you know. All right, Matt, what do you think?
You take a GCC compiler and you put it together and you run it.
Great. Yeah. So you are already 25% of the way through this talk. Okay. But yeah, I mean, you have to, like, for those of you who don't know, who aren't sure if they know, you can't just run this. And when I say just run this, I mean, when you take something like, who here is, raise your hand if you're familiar with Python or Perl or JavaScript or Racket even, technically. All of those can be executed by your computer from the text that you write. This text cannot be directly executed by your computer. You have to compile it. So assuming I have some bash shell, some Linux shell that I can type commands in, or a Windows shell like PowerShell or command prompt or whatever, I could run this, but first I'd have to do some compile steps. So why? Like, why can't I just run this? Like, why doesn't /main.cpp work? Well, the first problem is that, let's think about the / part. So who knows what /? If I'm on Linux and I type / something, what does that do? OK, so that is bash notation for current directory, a thing, run the thing. So bash will try to run it, run whatever program you give it if you type /main.cpp. So, and this generalizes two other things. So, like, for example, you're all familiar with the ls command? OK, that's actually user bin ls. Oh, sorry, /bin/ls, right? If ls were in the current directory, I could do ls. So if I cd bin, it's running ls in the directory that I'm running it in, right? So there's nothing special about the fact that it's main.cpp. So why doesn't this work? Like, why can't you just say, run this code? Well, the first problem is that bash doesn't know it's C++, right? So when you run ls or cd, which is apparently not in this folder, but like you run grep or whatever, you run one of these programs, it knows that it's an executable, like it's a binary executable, because of the way, so there's no file name. That's one thing. There's no extension, and it can also see by reading the first few bytes of the file that's executable. It can check the execution bits, et cetera. But if you don't do any of that, it's going to try to run it like a bash script. So if I had some like bash script, does everyone know what bash is? OK, it's a script. Well, the bash scripting language is a scripting language for the bash shell. So this is the bash shell, which is the shell that anyone who's ever used Linux has used, almost certainly, maybe sh. But when I try to run something, it's going to run like bash. And this is going to work, but this isn't, because that's C++, not bash. So that's the first problem. But let's say you could look at the file extension and be like, oh, it's C++. Would it work then? Well, no, because fundamentally, C++ is a compiled language. So it could be like Python, but it's not. We say things like Python are interpreted, and we say C++ is compiled. Because unlike Python, there's no executable. Like the Python executable is what takes your text Python code and runs it. But for C++, there is no executable. There's no program that runs your code. You're trying to run the code directly. Does that make sense? So when you write Python or what scripting language have you used, Tom?
Java. OK,
close enough. The Java virtual machine will. There are scripting languages for the Java virtual machine, like Groovy, which is Java but scripting. Have you ever used that? Okay. Do you see the distinction here? It's like there's a program that can run your text, that can read your text, parse it, and do things, whereas with C and C++, we're trying to get actually a program that can run directly on the CPU. Okay, so, and the last 2 points are just to go a little bit deeper into like why this isn't possible and like why there are languages that are like this. One is that it varies between projects, so the way you compile code is not the same for every project. So given a dump of C++ source files, how you compile them is incredibly complicated and changes between projects. Some of it is just like what developers like to do. Like, am I going to make a library, or am I going to make everything into one executable with no extra libraries? But some of it is like this chip requires different compiling options than like this thing. So like my laptop versus an Arduino versus like some ARM chip. Like they require different things. And fundamentally, that's because some of them have different instruction sets. So like the lowest level commands that the CPU can execute are different. Has everyone taken either an embedded course or systems or machine organization assembly language? Okay, you haven't taken it? Okay. Fundamentally, CPUs can do certain things, like they have certain assembly instructions that they can execute, and those are not the same on every computer.
Right.
So when you have a compiled language, the way you compile it is not the same for everything. There's no simple way to run it like there is with Python, right? Or Java. The same Java code runs everywhere. How is that possible? It's because there's another program that's running your program for you. So there's a Java virtual machine that's written for each different computer, each different architecture, and that runs your code instead of the code running directly. So is it clear why ./main.cpp does not work? Does that make sense? Okay. But could it? Disclaimer, don't do this. Probably. This is probably a really bad idea. But unfortunately, it is possible. OK, so I'm going to go through this line by line. There's nothing really magical here, but it does require some basic knowledge of Bash and C++. And I know we're kind of weak on Bash. So let's start with the first line. If this were Bash, if I were my Bash shell trying to run this as Bash script, does anyone know what that first line would mean? OK, in Bash, # is a comment. So that's a comment. OK, so I ignore that line. Next line, g++ main.cpp. What does that do?
It compiles the main CPP file.
Great. So if I'm Bash, I'm going to see that line and be like, great, I'm going to call the g++ program. My argument is main.cpp. I'm going to compile it. And by default, it compiles it into a file called a.out, which is just for historical reasons. So, oh, shit, I forgot to start the recording for the screen. OK, that's going now. That will build a.out, and then the next line, what does this do? So you can just, someone just say it.
Does terminate the program?
Terminate? You mean like execute?
Yeah.
Yeah, it runs the program.
Yeah, or
So,
it runs it.
yeah. So it runs, well, this, oh, were you thinking I said exit?
Yeah.
Yeah, no, sorry, yes, this terminates the program. So you compile a.out, you run it, and then you exit. Now, because Bash is a scripting language, and it literally goes like line by line and executes things, none of this ever gets executed by Bash, which is great news because this is not valid Bash. So now if we review this file, if we look at it again, but as if it were C++, what would we see? So if we're looking at this as C++, what is this?
Preprocessor.
It's a preprocessor command. So have you ever seen if-defs or #defines? There we go. There's an if. Now, it just happens that it's always false, but bear with me. If false, a thing, and if some yield C++, right? OK. The preprocessor, when it sees this and this, is never going to try to parse these 3 lines as C++, because we told it not to. So it's going to ignore this, and the rest of this is a valid C++ program. So essentially, we've managed to create a file that is, at the same time, both a valid Bash script and a valid C++ program. Not only that, the valid Bash script that it is compiles and runs itself. So demo time. Just to prove that I didn't cheat. That's what it is. The only difference is I've called it .secret main instead of a.out. I just changed the file name. That's the only difference here. You'll notice that it's green, so I have already set the executable bit. So normally if you were to just write this in a text file and just save it, it would not be executable, so this would not work. But we can just fix that up. There we go. So again, there's no magic here. It really works. Now, I think this is pretty clever, but we can go even further. So let's jump back to the terminal here and look at a slightly more complicated example. So again, basically just main.cpp. There's a build folder and a cmake list folder, but let's say we ignore those for now. I can actually remove the build folder. So here's a program that calculates the square root of whatever number I give it. But it's C++ code, but I ran it with /main.cpp. There's something wrong here. How is this possible? It's the same trick, really, but with a slightly more complicated bash. So, here's a C++ program. So if we view this as C++, it's exactly the same. We've got an if and def bash, or this could be if false also. And we've got our valid C++ program here from line 17 onwards. And in the middle, we've got just more bash. So in this case, I went so far as to use the app package manager to install cmake and my compiler, G++, just to make sure you have it. Make a build directory, enter the build directory, cmake ... make. So basically, the same general principle, and then it runs it, of course, with all the arguments provided on the command line. So I don't want to justify this as like a thing that you should do, but it is very cool, and it makes you think about like what it means to be a compiled language, and like the fact that you can't run it, but you actually can because some bash trickery. I could argue that this is good because if you're an open source C++ project and I'm a new C++ developer, and like Tom, maybe I don't know how to build your project. It's like, of course not. How would I know that? And so you as the developer could provide some wizardry like this such that I can actually just run the program that I think I want to run, and it will build it and run it for me. But my point is not to justify this crazy hack that I've come up with. It's really just to talk about C and C++. So yeah, this is really the line that we've been missing this whole time. Right? We understand why /main.cpp doesn't work normally. We've seen a fun, hacky way to make it work. But really, we just wanted this. Right? We wanted a compiler to compile our code into binary machine code that we can actually execute on our computer directly. But surely, none of you know all of the steps that make up this one magical command. And boy, are there a lot of them. Why is it important? Well, there are a few, and I'll go through 3 concrete examples, a few ways in which understanding how this works will make you a better programmer, make you be able to debug things faster is the main thing, optimize your build system so that your code compiles faster, among other things. So what does that do? Well, it does all of this. So let me back up one step and explain the project we're trying to build here. So we have an executable, main.cpp, a small library, which is lib.a. It's made up of 2 different files, foo and bar. If we want to see the actual contents of this, no. Right, so we've got main.cpp, which just calls 2 functions. We've got, there's one of the functions, and there's the other function. They just print their names, right? Very basic. So if you had these 3 files and their corresponding header files, which are like basically nothing, you could compile all of these things by just typing like g++ main.cpp foo.cpp bar.cpp. And magically, and like maybe like -o to say the output name to be like main, right? That would do all of the things. But what are all of the things? Well, there's 4 or 5 main components that you need to understand that they're happening. Now, how they work, that's way beyond the scope of this talk, and I personally don't know. But you have to understand that there's really 4 or 5 main steps. So the first step is the preprocessor. So we saw this trickery used in our little demo from earlier, but the first step is to take your C++ source file and run it through the C++ preprocessor. So on a standard Linux GNU C++ toolchain, that program is called CPP. So there's an executable called CPP, which will take in your source file and output your preprocessor file. And these file names are, file extensions are like the canonical file extensions used. They don't make any sense, just accept that they are what they are. So .ii is preprocessed versions. So this will always be the first step. And so we do this for each of the 3 C++ source files we do independently. The 3 most important things that happen during that step that you absolutely need to understand are a part of that step are 1, pound includes, 2, pound defines, and control statements like if and def, if and def, if else, those kinds of things. So anything you see hash, whatever. So pound defines, we all know what those are? OK, so those values get substituted in this phase. So if you have pound define x 5, wherever there is x in your code will become 5. And it's very dumb and very blind. It will literally, I mean, it's like basically string replacement. So if you pound define x and you have yeah, this is why people are worried about like reckless pound defines, like pound define min, right? If you do pound define min and then function that computes the minimum of 2 things, now anytime anyone writes min, now it's the function. So not great. But that's the first step. And it also expands all your pound includes. So if you do like pound include stdlib.h, right? It literally takes the contents of that header file and expands it and puts it in that file. And it does this recursively, right? So in our example here, we have main.cpp includes bar.h and foo.h. And we saw earlier, this is what those look like, right? So if I look at main.ii, this is what the preprocessor generated. So these are just preprocessor comments, basically. So I mean, I don't pretend to know what all of these mean, but you can see here, basically, void bar func, I mean, that's expanded from bar.h, and the same thing for foo func. So the contents of this file was literally put in this file. And the same thing would happen for bar.h and foo.h, but they don't have any pounding. There's no preprocessor work to be done in those files. So that's the first step. Next step, we need to take the preprocessed C++ files and turn it into assembly. This actually happens. It actually generates assembly. Like sometimes we forget this, but you call the cc1+ executable, and you give it your preprocessed files, so the .iis, and you say, what's my output? And .s is the extension used for assembly. And you get real assembly. We can see what this looks like. So we have, again, we have this as our main.ii. We can also look at foo.ii. Super long. Actually, let's back up. Can anyone tell me why foo.ii is super long? Here's what foo.h looks like. Wait. Hold on. Here's what foo.cpp looks like. There we go.
Because of the IO stream?
Yeah. What is line 1? Include IO stream. Uh-oh. That's probably a big file. You ever thought about that? That file literally is now in here, and anything that included. So like, I'm not so lucky. It's there somewhere. We can find it. And I assure you that it is a long file that probably includes other things too. Yeah, there we go. So like, oops. Yeah, so yeah, it's that's a file. It's got 79 lines and probably includes other things. Yep, see, look at all these other includes you got down here. Line 38, right? So all of those get expanded and put into foo.ii, hence why it gets so long. But just looking at main.ii, which is relatively short by comparison, we can also look at the assembly for that. Now, I don't pretend that this means anything to any of you, but like, this is what assembly looks like. You've got some like move instructions, some call instructions, etc. And you can see actually there's kind of useful names. So you kind of see that this line kind of corresponds to this line, and this line kind of corresponds to this line. These are mangled C++ symbols, so it's not like totally clear, but this is the real assembly that gets generated. And then the next step is to compile that assembly into what's called an object file. So .o, file name actually makes sense, or file extension actually makes sense, which is great. And what is .o? Let's see. Does anyone have a guess what this is going to do? What it's going to look like? Ugh, it's binary. We can't. That's not text. So we finally moved from text assembly to object code or machine code. So there's a lot of stuff that is human readable just because the object file format has information on the thing that it was compiled from. So like it says like the architecture, what it was built on, Ubuntu, blah, blah, blah. It's got a bunch of other, you can see there's like some symbols, some mangled symbol names there. But this can be run by the computer, almost. So this is just the object file. This is not the final executable, but it's pretty close. I mean, it is now machine code. So the last step is to the last step, I'm skipping one temporarily. Last step is to make the executable. In this case, because we're also building a library, we need to combine foo.o and bar.o into a library, and that's what's called archiving. So there's AR, create library, blah, blah, that really, almost literally, it just concatenates the files. We can see this for ourselves if we do cat foo.o, cat bar.o. Let me make this smaller. I know you're not going to be able to read this, but this will just make it. And then if I cat lib.a, you can see like it's basically the two things stacked on top of each other with a little extra fluff at the beginning. But basically, we have to combine these two, so we archive them fine. Then we want to take the main.o object file, lib.a static library, which I don't know if it's technically correct to say it's also an object file, but we need to combine those two. So that's what this line does. Now, there's a lot more in this line, but in this line, you can see at the end of the line over there, there's main.o and lib.a. So the rest of this stuff is a bunch of other object files. You can see there's crtn.o, crtbegin, crti, ldlinux.so2. Now, I don't know what all these things do, but they define different symbols that are necessary to get an actual executable. So unfortunately, I can't explain exactly why all of them are necessary, but this is the minimum you need. Anything less, you get unresolved references or other things. I think it's just like a bunch of I don't want to say boilerplate, but a bunch of things that you never see as a programmer, but that GCC will link against for you automatically, which is great. Like no C++ programmer I know is going to know what all these files they need to include are. It took me like half an hour to find all of them and like figure out like that these are the ones that you need. And then of course the other two things that we all know that you need are libc and libc++. So these are the C and C++ standard libraries. So we're calling like IOStream print functions, and those are defined in there. So we need to link against those. But basically, this step just crams together our object files and our static library and our standard libraries into an executable. And I mean, for fun, we can cat that, but it's not, I mean, it's like not that interesting or understandable. But yeah, so those are all the steps. Any questions? I'm sure you're somewhat overwhelmed, but any specific questions about these steps? What's up?
How does the assembler find the STD lib if it's not touched until the last step, which is thinking?
It doesn't need to. So if we look at the assembly for example, food.cpp, which is the one that actually calls that function, I mean, it's long, but it's not that long. You can see all it needs is call IOStream blah, 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 blah. And this is actually a great time to show off a cool tool that you all should hear of at some point. It's called C++ Filt. And it will take a mangled C++ name and unmangle it for you. So this call of that is actually this thing. So it's IOStream, the double arrow, left shift if you want to call it, operator. So the assembly just calls that. Now, on its own, like if you didn't link against libstd++, once you tried to get to that last step, this would fail. It would be like unresolved reference to that thing. But you don't need it at that step. You're not requiring the code, the assembly code, or the object code even, to be present and known at that point. Which is why C++ has like headers and like function definitions, because you basically don't require the actual code for the thing you want to call to exist until like the very last second. And up until then, you just rely on the definition to generate the right call. And we'll see an example of that if I move on. OK. All right. We're going pretty slowly here, so I'm going to try to move on. Handy chart, courtesy of that link down there. Great blog, by the way. That person has been working on the GCC compilers for a long time. This just shows the file extensions and the programs that make them. So like if you have a .cpp file, you use the CPP file to get the preprocessors, et cetera, et cetera. And of course, these slides will be in the link in the description in the YouTube video, and I'll post them in the group too, so you guys can have the slides for later. And if you're curious how I figured out all of this insanity, I just did this. So I just told GCC to be verbose, and it prints out like pages and pages of stuff, and then you can like delete stuff that you know is not necessary if you like kind of know what you're looking for, and you can kind of distill it into this. OK, so far we've talked about why you can't do /main.cpp, why you can't run C++ code natively, like just as is. Then, OK, so if we have to compile it, how does that actually work? What are all the steps to that? So those are what all the steps are. But how is any of this useful to you as a roboticist or as a software engineer? And I'm going to go over 3 concrete examples. So the first two are debugging examples. So imagine you're at your desk, you're writing some code, you compile it, and you get an error. Your ability to resolve that error quickly is a function of how well you understand that error. And so I'm going to go over two very common errors that I hope you have encountered, and how understanding the things that I've gone over today mean you can immediately solve the problem, or at least much more quickly than your counterparts who have no idea what it means and just Google it and look on Stack Overflow. So first one, undefined references. All right, so does anyone want to try to tell me what an undefined reference is? OK, no one's so brave. That's fine. Let's look at it in an actual example. So let's say we've got main.cpp, all right? Just calls a function. Does this code make sense to everyone? Like, no one's confused by the lib : We all know what that means? OK, so yeah. And then lib.h, it's just a function, and lib.cpp, there, it just prints a thing. It's in the namespace lib, yada, yada, yada. So if I run make, we'll build this program here. You can see, I'll show you what my make file is. If I do make broken, that's not what it's called. Make main broken. I will get this lovely undefined reference. So what make broken does is it calls, so if I were to run this, g++ main.cpp -o main broken. So right, I have my 3 source files, and I do this. Does anyone know what's wrong? Just like off the bat. Okay, so notice in this line, do I mention foo anywhere? No. Main.cpp. So again, according to our knowledge of how the compiler works, or the compiler driver, which is really what G++ is, what's going to happen? So first, preprocessor expansion. So it'll expand the pound include for foo.h. So it'll add the function function declaration for foo.h. Void, foo, whatever. No body, just the declaration. Fine. So then it compiles it into assembly, compiles it into object code. No errors so far. Then we get to the linking stage, when we try to combine all our object files, but in this case, I haven't given it any other object files, so basically we're just trying to turn main.o into main, the executable. We get an error. Let's go line by line. So /temp cc blah, 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 .o. What is that? That is the temporary object file that G++ created when it was compiling it. It makes it in your temp directory because it's trying to be nice and clean. It actually deletes it, but there's a flag in GCC. You can tell it to keep it around if you want to look at it, which is super useful. It's like -- keep temporary files. But so this is meaningful. It's not meaningless. That's the actual file, the object file that it was looking at the time in function main. Okay. Main.cpp text 0x10. So that refers to the position of the function so .text is the code, like the text code in the object file, and that's the address of it. But basically, it's in main.cpp, okay, and there's an undefined reference to libfunc. So what's a reference? Well, it basically is any time I can't define it without using the word reference, a symbol. So whenever in main.cpp, somewhere I talked about libfunc, in this case, I called that function, right? And that reference is undefined. Well, you should ask yourself, where should it be defined? So where is libfunc defined?
Foo.cpp?
Right. That's where I wrote the code for it. That's where it's defined. So if we were to compile that file, eventually it would be in some foo.o, right? But we didn't say anything about foo.o. We didn't tell it that here's foo.o. We didn't give it to it. So that reference is undefined. Does that make sense? So all we need to do is tell it about foo.o. In this case, that's as simple as adding foo.cpp, or sorry, I did many steps. Okay, but basically, so we compiled lib.cpp separately, and then added lib.o. But of course, we could also just do oh, I've been using the wrong name this whole time. It's lib. I apologize. And now it's not broken. So of course, main working, it works. So does that make sense to everyone? So the function definition is in lib, but I didn't give it lib. So the definition is not there. So my reference is undefined. Cool? OK. I'm going to skip this other example. We can come back at the end if y'all aren't kind of exhausted by all this. It's a little more complicated. I don't think you guys have run across it before. I guess I'll just check. Has anyone seen this error before?
Probably.
Well, OK, fine. Let's go over it. So this one's pretty similar, but it's longer, and there's a different error. So what do we have here? So it's now saying undefined reference to another function. OK, fine. But now below, it also says undefined reference to vtable for class. I'm going to assume no one knows what the vtable is. So vtable is a virtual table, which all I know about it is it's a table that gives you all the addresses of all the virtual functions. So do we know what a virtual function is? Okay, virtual. So if you have a class in C++ and it has a virtual function, that means that function can be like overridden by subclasses or whatever, but like it needs to have some definition somewhere, either by the class or a subclass or whatever. So in this case, we have the class. Here's this definition. It's got one function that's virtual, and right now I have commented out the. Sorry. We have a declaration of a function, which is virtual, and its definition is commented out. Okay? So if I try to compile this, and again, I'm just using this. So I'm giving it all the files. Notice I didn't leave out class.cpp. I was not so silly that time. But still it errors, because I commented out the definition. So why do we get this and not like something useful like definition not found? Well, because when you compile these two functions, so let me also show you vtable. It's pretty trivial. It just creates the class and calls the function. This is where we get the first error, right? So once we get to trying to mash the two object files together, we have one object file, which is this guy, and then we have another object file for class, but because the definition is commented out, it doesn't actually contain the definition of that symbol, aka the class func reference will still be undefined, because it's not in lib.o. It's not in the class.o. It's not in the object file of class because it was commented out, right? Does that make sense? So the other error we get is undefined reference to vtable for my class because it was a virtual function, and the virtual function had no definition. There's now a reference to the vtable. Like by calling this function, I am actually requiring the compiler to look up in the virtual table what the address of the virtual function is, because it's not straightforward. It could be defined in somewhere else. It's not as simple as a normal function. So it has to look up in the vtable, but there is no vtable because it couldn't make the vtable because one of the virtual functions of the class was undefined. Does that make sense? So if there was another virtual function for the class and it was defined, we'd still have this problem because you couldn't create a complete correct vtable for my class. So again, this may be a little bit too detailed, maybe a little over your heads, but knowing that there are object files and they contain symbols and you can make them independently and then match them together at the end, and it's the linking phase where all of this happens, knowing that gives you a big leg up in fixing this stuff. Is it clear why understanding that like you turn source code separately into object files and then you put the object files together allows you to understand, and knowing the terminology, like knowing what reference means, knowing what undefined means, knowing what a symbol is, knowing what an object file is, all these things make these problems wicked easy. Like I know in my own personal experience, like before I understood all this stuff, at least to the level that I do, I don't pretend to fully understand it. Undefined references meant an immediate Google search, which of course is useless because the only part that you're Googling that's similar to other people who's had this problem is undefined reference. You're not going to have the same symbol that's undefined. So you're almost certainly not going to find useful code or useful answers, especially if you've written the code all of yourself. So it's good to understand how all this stuff works. The next example I'll go into is on a different error. So here I've got main.cpp, which again, this time it just calls two functions. So pretty straightforward. Lib and bill. So again, really trivial, just prints out the value of x. And x is defined in bar.h. So that's why each of these include bar.h. Bar.h, basically just think of it as this. So I have some preprocessor stuff to like make it so I can fix it with a different command line thing. But basically just assume it's int x equals 2. So if bar.h was x equals 2, you might expect this to work, right? So you'd have this function which includes bar.h. Great, so we have x there, so we can print its value. Awesome. Same thing in this file. We can get bar.h. We can get x from bar.h. We can print it. And then here, of course, this should work. We're just calling two functions, right? No. So if I try to build this, and the way I'm building this is the way you would expect to build this, which is just you give it all the files, and you give it G++, and you say go. So this should work. You should expect this to work, unless you're really thinking about the different steps that are taken. At that point, you can understand why there's a multiple definition. So again, line by line. Boop-a-doop. First of all, notice we have two object files now, so two temporary object files. So that should immediately remind you of, or indicate to you that we have two separate things that are being compiled into object files. One of those is going to be lib.o, one of those is going to be build.o. So you should be aware of that. And then the actual text of the error message is multiple definition of x. So remember, what is a definition? So definition is it's basically the equals to part of int x equals 2. Or for a function, it's when you have the curly braces and the actual code in it, as opposed to just the semicolon. That would be the declaration. This is the definition. So this is saying x is being defined twice. Well, that's stupid. I wrote int x equals 1 once, right? So how is it being defined twice? Again, go through the process. So we have lib.cpp and build.cpp. You run the preprocessor stage. What does that do? It expands all the pound includes. So that means, actually, I think I can do this. That was a mistake. All right, no, we're good. OK, ignoring all the IO stream stuff, this is what this now looks like. So we have a function definition just as we wrote, and it expanded bar.h, and now we have int x equals 2. But of course, Bill is going to look the same, right? So now, think about it. We have two preprocessed files that turn into assembly, turn into object files. Now we have two object files, totally separate. They don't know anything about each other, that have int x equals 2, the code for int x equals 2 in them. So then what happens at the linking stage when you try to combine them? So you have main.o, lib.o, and build.o. You try to put them all together, try to link them all together. You're going to get a multiple definition of x, because you have two object files that both define x. So do we understand why that's an error? OK, see, it sounds so obvious when you go through the steps that way, but intuitively as a programmer, when you're writing these things and you pound include something here, pound include something here, you're like, well, obviously it's the same thing. It's the same bar.h. But it doesn't know that. So that's going to be error at the linking phase. And if you understand the preprocessor is literally expanded and then compiles the object files separately and then mashes them all together, you can explain this to yourself fairly easily. So how do we fix that? This is not something you can fix by understanding this process. It's kind of like a separate thing you have to know. But I'll show it because of course you want to know it. No. So the way we fix this correctly is the only difference here is we add this -d_fixed, which basically makes bar.h become x turn into x instead of int x equals 2. So if instead of writing int x equals 2, we correctly wrote x turn into x, this is only a declaration, not a definition. Make sense? So when you compile lib.o and build.o, you don't have two definitions. In fact, you have no definitions. So the naive step, if you just add this defix, if that was the only difference, you get a different error, the same error we saw before. Now you would have an undefined reference, but you would have it twice. Why? Because you now have two object files which reference x, but there's no definition for it. So you're going to get an unresolved reference to x. OK, we just shifted our error. So the last piece of the puzzle we need is we need a definition of x once. So we have our two object files and also main. These both define x. They know what x is, but we need something else that they both declare x, but we need something that defines x. And we can't put it in bar.h because then it will be in both of these. So the thing that you do is you just make a bar.cpp. You have a third thing. So now we have, and I didn't show this to you until now because I mean, that's part of the evolution. So this file is empty when you are doing it the incorrect way, but it includes the definition of x when you're doing it the right way. So basically, we have two object files that include one header. That header simply declares x, and then the definition of x is provided once in a separate source file, bar.cpp. And then you compile all of these together. So we've got main.cpp, bar.cpp, lib.cpp, and build.cpp. So bar.cpp is the new one. What is it then? Now it works. And x equals 0. And you notice that's different, of course, than when I had x equals 2 in there, because that was the old example. So does that make sense? What's up?
How does this differ from the include guard?
Ah, OK. Great question. So maybe you're saying to yourself, oh, wait, I heard about this thing called include guards. That's going to solve my problem, right? So you go over here. Let's say it looked like this. And you say, ha, got it. What has that done? So, well, or maybe in systems you saw like if and def, guard, define, guard, and if. Maybe you saw that instead. So what does that do? Let's run through it. So let's say you're compiling lib.cpp. OK. You read lib.cpp, which includes this file. So you expand this file. And then you look in this file, and you see if and def guard. Guard's not defined. Great, define guard. Then you say int x equals 2, and then you end it. So now you have lib.ii, which, heck, let's do it. So let's say this is what that looks like. So I did that for bar. So bar.cpp -e. OK. So you can see now we have, wait, bar? Oh, no, wait, hold on. I didn't want to do that. Wait. What file is this? Bar.h. Why is this bar.h? Hold on. Have I been using the wrong names? Bill, lib, bar. Okay. Yeah, sure. So I want to do this is the same. Allow me to submit that this is the same as the header guard. It's just a GCC specific magic. So now I want to compile preprocess lib. OK, so see any difference? Let's run it again. So keep that in your mind. Same. It didn't change anything. Should it have? No. Right? What were we going to say?
Oh, I thought this time it only has that int x equals 2 on one of them, but never mind.
Yeah.
It was like it the last time.
It's the same. This does not solve our problem. All this does is prevent, let's say, that. So if I do that, then it will only do it once. So I don't need to demonstrate that, I think. It's pretty clear that pragma does not solve any of our problems. What? OK, so we've gone over two examples, one of multiple definition and one of undefined references. The last example I want to get to is an example of optimizing your build. So when I say build, I refer to all of the steps of compiling. And usually in a sufficiently large project, you'll have some build system like CMake or Mason or Bazel or whatever. And you have a lot of source files and a lot of header files, and you're going to build them, and at some point, you're going to realize, gosh darn it, this takes like a minute. Every time I want to compile my code, this is really annoying. If you don't know any of the steps to building, what could you possibly do to fix it? So I have an example here, which I think is very simple and elegant, and maybe hits close to home for some of you. I know it does for me. No, where is it? Reckless headers. OK. So let's say I wrote this code. Includes gazebo.h and calls a function from that header file print version. So gazebo is a robot simulator. Everyone who's taken 2002 knows what that is. For those of you who haven't taken it, it's like a simulator. It's like this big, complicated robot simulator, and it's got like a C++ interface, and you can like do all this stuff in it. Anyways, so you're naive, and you do this, and you run it, and you let's say you're using CMake. There's nothing complicated in here. You just do make reckless headers. What the heck? What is it doing? Why did that take so long? All the other examples we did took like you couldn't even count. Like it was like instantaneous. So why is this so long? Well, let me explain by comparison. Here's like the same. This works exactly the same. It functions exactly the same, but instead of actually including gazebo.hh, I just do this little trickery, and I give a copy the function definition, basically, right? Because that's all that's in the header that I need is the function function declaration for print version, right? It's just a simple void function in the gazebo namespace. OK, so they do the same exact thing, but I'm going to have to. That one is fast. So it's crazy to think, or at least it was to me at first, but pound including a file that you don't know what's in it can dramatically affect your build time, because it turns out gazebo.hh includes literally every include file in Gazebo. Like it recursively includes all the files in Gazebo, which also recursively includes a bunch of files from Boost, which is this huge C++ library. So just the pre-processing step, because of course after the pre-processing step, there's very little code. It's not like you're compiling all of Gazebo, but the actual pre-processor step itself is so time-consuming that it can dramatically change the build time. And I know I'm out of time, but let me just prove it to you. This is not a one-off example. I'm going to run it a bunch of times each time. So OK, 4.8 seconds. 4.7 seconds. 4.8, 0.6, 0.6, 0.6. So again, understanding all the different steps can empower you as a programmer to fix bugs faster, to improve the speed of your build, and also to sound really smart when you're talking to your coworkers. Thank you.
Does the namespace check cause incompatibility issues when the library updates their code?
Oh yeah. Oh no, you should never. To be clear, do not do that. That is just the quickest example I could come up with. Do not look at the header file and copy the function definition. No. That's not the right solution. In this case, I would argue the right solution is, well, the right solution for me as an end user is to use pre-compiled headers. So I will pre-process the headers once, and then it will smartly check if they've changed, it will recompile it or whatever. That's the real clever solution is for Gazebo to have better header file inclusion, such that that basic function is not recursively including literally thousands of files. But it's hard to do that in any sizable project. It's really hard. So I would argue pre-compiled headers is a solution. That's what I use personally. But yeah, there's a lot of even something. That example is really driven by you're working on a big project. You're sloppily coding away, and you leave headers in that you don't actually need. Those headers that you don't actually need can be killing your build time. for literally no reason. Because it has to preprocess the whole file, because it has no idea what you're actually using in it.
Is there a particular reason why it went faster? Did it like automatically realize that they need to include all that stuff and
Oh,
optimize it?
sorry, I totally didn't explain that. The first 3 times are reckless, and the second 3 times are careful.
Okay.
Yeah, so this is the difference. It's an 8 times speed up between doing it the stupid way and doing it the hacky way, but like good dependent, you know what I mean? Like, yeah, I'm not saying that you should actually do that. I'm just giving an example of how slow one header file can be.
All right, thanks.
Yeah.
So you mean that to execute Python file, because we have an interpreter like our OS, right?
Or what?
We have an interpreter in the OS so we can execute Python file. Why don't people make an interpreter for C++?
Great. I tried to get to that, but basically it's because of kind of like these last few reasons. So the reason you want a compiled language is because it's way faster. When you're executing assembly instructions or object code, machine code directly, it's incredibly fast. And so could you write an interpreter for C++? Yes.
JavaScript and
Yeah, there's actually there's an existing thing that allows you to take C++, compile it to assembly, and then convert the assembly to JavaScript, and then run the JavaScript. So there's still a compiling phase. I mean, C++ as a language is not designed to be interpreted, like Python is. Yeah, there's probably a way to make C++. There's probably a thing that will convert the C. But like the point is, C++ is designed to be a compiled language just because it's faster. It could have been designed to be a scripting language like Python or Perl or JavaScript or whatever that can be interpreted. But as is, no, you cannot just write an interpreter for C++. And it wouldn't even make sense because there's like things that you can write in C++ that like that are like hardware specific. Like, what would it mean for me to say like I'm going to set this bit in this register to 1? And then I want to run that on like my Raspberry Pi and my phone. Like, it doesn't make sense. So you can do things that are hardware specific because you have a hardware specific compiler and like all this like specific stuff that's like much higher performance and like specific to your hardware. So it's sacrificing like portability and like arguably ease of use for a bunch of great advantages like speed and speed. Cool.